All right, folks. So I'm going to talk about page 2 of the final exam review. What you didn't get to see is I was about halfway through talking through all this, and then my computer turned off because, of course, even though I've been doing this virtual school thing for almost a year, I still sometimes forget to plug in my laptop. So I just wasted about 7 minutes. Let's not waste any more time. Let's get right into question number 4, 5, 6, and 7 on the page 2 of the final exam review. So question number 4 talks about an object with an initial velocity of 70 meters per second and a constant acceleration of -1.5, which means this object is slowing down. We want to know how far does it travel if it does this for 9 seconds, right? So what does the graph look like, first of all? Well, the velocity graph starts out at 70. It decreases a certain amount. Okay, so at some point here, we'll have to figure out what is the total change in velocity here. And we know how much time it moves for. We know that the total time traveled is 9 seconds. Okay, so I guess what we need to do next is figure out what is that change in velocity. And we can figure that out by recalling that the change in velocity is equal to acceleration times time, right? So acceleration times time is going to be, 9 times -1.5, which is -13.5. Okay, so what that means is the velocity of this object changes, right? It decreases from 70 meters per second to 70 minus 13.5. So we can actually figure out the final velocity is going to be 70 minus 13.5, which is 56.5 meters per second. Okay, why do we need to know the final velocity? Well, we need to know the final velocity because if we want to know the area underneath this rectangular portion of the graph, I need to know what is the height of the rectangular portion of that graph. And now I know it. It's 56.5 meters per second. All right. Okay, so now where are we? I think we have everything we need to know to get this area. So let's start with the rectangle part first. The area of this rectangle is going to be the final velocity times the time, which is 56.5 times 9. 56.5 times 9. I should know this because I just did it like 10 minutes ago. 56.5 times 9 is 508.5 meters. So 508.5 meters. All right, great. Let's do now the triangular part. Okay, the triangular part is going to be, let's see, the change in velocity is the height of it. So that the area, which is the distance, is 1/2 times the change in velocity, which is 13.5, times the time, which is 9. Okay, let's multiply this out. 13.5 times 9 times 0.5. Yeah, 60.75 meters. 60.75 meters. So that's the triangle part. Can't you really see that? There you go. So yeah, triangle part, rectangle part. Total distance then is going to be the sum of this and this. So if I add 508.5, I get 569.25 meters. And that, I believe, is an accurate answer for question number 4. We are now ready to move on to question number 5. So let's do that. All right. So question number 5 is about a boat. And we know a lot of things about the boat, but we do not know what its initial velocity was. That's what we're trying to figure out. What is the initial velocity of this boat? If we know how far it goes, we know that it has a particular acceleration. We know it accelerates 2 meters per second every second, and we know it does this for 3 seconds. Okay, so time is 3 seconds. Okay, once again, as soon as I see a shape like this for a velocity time graph, I immediately think about the two different parts of it, the rectangle part and the triangle part of it. Is there anything else I know? Oh, yes, I do. Okay, one other thing I know here. Since I know the amount of time that it moves for, and I know the acceleration, I can figure out the change in velocity by multiplying time times acceleration. So the change in velocity is 6 meters per second, which is going to be useful even if I don't know what it started out at. I do know that it ends 6 meters per second faster than it started. So that's cool. All right, now what do we do? So I guess what we do is let's figure out some expressions for the areas here. Okay, starting with the rectangular portion. The area of this rectangle here would be the initial velocity times the time, which is 3 seconds. We'll call that area number 1. Area number 2, which would be the triangle part, that would be 1/2 the base, which we know is 3, times the height, which is the change in velocity, so that's where it comes in handy. Okay, times the 6, and that's great. I know everything in this top part. The only unknown, it looks like, is the initial velocity, so I can put everything together. Total distance equals the initial velocity times 3 plus 1/2 times 3 times 6, which is 9, right? But I know the total distance, right? I know the total distance here because it says it travels 150 meters. So 150 equals initial velocity times 3 plus 9. And I'm just 2 steps away from solving this equation. So if I subtract 9 from both sides, boom, 141, and then divide both sides by 3, I get 47 is the initial velocity. 47 meters per second is the initial velocity. Okay, and it looks like that's it for question number 5. Okay. All right, question number 6. This is another one that I know we've seen before. Okay, a skateboarder kind of skating down a sidewalk. The skateboarder starts with a certain initial velocity, has a certain acceleration, and we want to know if she travels a total of 40 meters, then how much time will that take? Okay, so this one I know is going to end up being kind of tricky mathematically. And so with this one, I'm going to set it up. I'm going to get to a final equation, and I probably won't solve that equation. I'll probably just leave it there, and then we can talk about that a little bit in virtual class if you all want to. But here's what it looks like. Okay, my board's getting a little. There we go. Okay. So rolls down the. Okay, initial velocity. V and T. Initial velocity is 6 meters per second. Slowly accelerates at a rate of 0.8. Okay. Unfortunately, we do not know the amount of time, so that's why I'm just putting a T there, where the dotted line hits the time axis. What else do we know? We know. Well, I guess we know the change in velocity, kind of, right? We can come up with an expression for that. The change in velocity is acceleration times time, which in this case would be 0.8 times t. Again, we don't know the t. We don't know the time, is what we're trying to figure out. And so I have to leave change in velocity as just 0.8 t. Okay? The last thing we know is we know the distance traveled. The bottom of the sidewalk, the end of the sidewalk is 40 meters away. So this area, which I'll call area 1, and this area, which I'll call area 2, area 1 plus area 2 has to equal 40. Has to equal 40, right? So now I just have to get some expressions for these. Let's start with area 1. Area 1 is a triangle. So the area there is 1/2 times acceleration. Well, let's see. Base times height, right? 1/2 base times height is the area of the triangle. The base is t, and the height is 0.8 t. Which I suppose if I simplify that, that's going to be 1/2 times 0.8 t squared. I can even take that a step further, and I can say this is 0.4 t squared. Okay? All right, so what about the area 2? Area 2, that's a bit simpler because it's a rectangle. Base times height is going to be the initial velocity for the height, which is 6, and the time is t. Again, we don't know t, so that's the best that we can do. Area 1, here's the expression for that. Area 2, here's the expression for that. Okay, and if you've gotten this far, that's pretty good. There's just a little bit more to go. I think I can see, yeah, we can see the stuff that I'm doing over here. So let me just kind of scoot it, and let's put it together. We have A1 plus A2 equals 40. 40 equals 0.4 t squared plus 6t, okay? So that's kind of the final equation that needs to be solved for t, okay? And again, when we've gotten to this point in the past, we've recognized that this isn't, you know, just a regular linear equation. This is actually a quadratic equation because there's a variable raised to the second power, okay? So solving an equation like this, there's a couple different ways we can do it. I'm going to try to use a calculator to do it. I'm going to use Desmos on my phone. But in order to do that, what I need to do is bring everything all to the same side of the equal sign. So if I subtract 40 from both sides, I get 0 equals 0.4 t squared plus 6t minus 40. And you might be wondering, like, why the heck do you do that? Well, the reason why you do that is because, and I'm going to open up Desmos. Boom. Well, there it is. Okay. And I'm basically just going to type in, let's see, 0.4 x squared plus 6x minus 40. And let's tilt the screen here. It's not going to work, is it? There we go. And it looks like this, right? So if I type in that equation, you could do this in your TI calculator, you could do this on Desmos on your computer, or if you have Desmos on your phone, you could do it like this. But you'll notice I'm looking for the two places where that graph crosses the x-axis. So if I zoom in, I can see that it crosses, oh dang, it crosses right where t equals 5. Okay, so what that means is t equals 5 seconds. That's the amount of time that this person takes when she rolls down the sidewalk, a total of 40 meters. So again, there's a lot going on here. The most important piece of it, right, the thing to kind of take away from this and to keep in mind if you see it on the final exam is setting up the graph, okay, knowing how to use the graph to get these equations, okay, and then putting these equations kind of together into the final equation. From that point, if you can solve the quadratic, that's great, and if you can't, that's not a huge deal. Again, if you have questions about that, we can talk about them when we see each other at 2 o'clock, okay? All right, one more to go on page 2, that's number 7. So let's see what number 7 is about. Alright. Number 7. So yes, this one looks familiar. A cyclist moving with a constant velocity of 11 meters per second passes the car that is just starting. The car has a constant acceleration of 2.5 meters per second squared. When and where will the car overtake the cyclist? Okay, so let's look at the two different scenarios. Okay, we've got the car and we've got the cyclist. The car is accelerating. Okay, so for the car, the distance that the car moves is given by the equation 1/2 at squared. Okay, the cyclist is moving at a constant velocity, so that's a simpler situation. That's just distance equals velocity times time. All right. The thing we're trying to figure out is when are these equal? When are these equal? So basically what we're saying is let's take the two equations and set them equal to each other. Right? Yeah, I think that'll get us what we need. And what's really nice about this is since there's a t on both sides, this t here will cancel with one of those t's there. And so really this becomes just 1/2 at equals v. All right, and I think if we solve this, we can figure out the t, which will allow us to figure out the d, and then we've got everything we need for number 7. So let's plug those numbers in. 1/2 a, what was a? Oh, 2.5 times t is equal to 11, which is the constant velocity of the cyclist. I'm gonna go back to my calculator again. It's still in Desmos. Let's go out of there. Okay, so 2.5, actually let's do this. 11 divided by 0.5 is 22, and that divided by 2.5, I get 8.8. T equals 8.8 seconds. All right, and if it's 8.8 seconds, then I can figure out how far away they are from where they started by just plugging in that 8.8 seconds into this. D is equal to 11 times 8.8 times 11, 96.8. 96.8 meters. So they the car is behind the cyclist up until 8.8 seconds has passed. It's taken 96.8 meters for the car to catch up to the bike, but after that, the car passes the bike and keeps going, forever, I guess. So that is the story for 4 through 7. I hope you enjoyed it, and I'll see you in a few minutes when we talk about the last few problems on page 3.